Okay, let's get another system in which we can calculate this factor omega 0. Let's just for simplicity, let's take the one-dimensional harmonic oscillator. We already discussed what the phase space looks like. It's basically an ellipse. Whose equation is given by p squared over 2m plus 1 over 2m omega squared q squared. This is equal to E. Or p over 2m e square root of E squared plus q over 2 over m omega square root of E, all of this thing squared. This is equal to 1. So this point over here is 2m square root of E. This point over here is q over, no, not q, 2 over m omega square root of E. So what is the area of this ellipse? Pi times the product of those two. 2 over m omega times 2m E. So m's will cancel. This is 4 pi over omega E.
Is it we have p squared over 2m and you divide it by E, and then you take the square root, right?
I just put everything under a common square. So I took the square root of E. There is this square root of E, and then I'm taking its square.
And then we have 4m squared, right?
Why 4m squared?
If you take this.
Well, you see, one is divided by m, the other one is multiplied by m. So the factors are, in the denominators is, here I have a m, here I have a 1 over m. When I multiply them, the m's just cancel. Now, of course, if you go back to our example, this is the area of the ellipse. And if you remember, what we do is we don't fix the energy, we give it some width. So actually, we should basically consider such a, well, I'm kind of exaggerating, such a ring. Well, I will take the width of the ring is again delta. And delta should be much smaller than E, and E is large enough. So the area of the ring which in our case is nothing but omega. This is just 4 pi over omega times delta. The number of states should be omega over omega 0. Okay, so some bad notation, let me call this some different omega. It's not the frequency omega. Which is 4 pi over, this is the frequency omega, delta over omega 0. This is the number of states available to my system. Now, if you look at the harmonic oscillator from a quantum mechanical perspective, the energy of my harmonic oscillator is given by h bar omega over h bar omega times n plus 1 over 2. So these are just equally spaced energy levels. So if I take a energy interval of length delta, the number of states in this delta energy interval is just delta over h bar omega. This is the quantum mechanical treatment, which should be equal to 4 pi over the angular frequency times delta over this omega 0, the volume for unit state. So you see omega turns out to be, in this example, in this one-dimensional example, it's just 4 pi h bar 2h. Now why is this factor 2? You see, if in our previous argument we had omega 0, if we have a particle, if we have a single particle n is equal to 1, we have h cubed. And cubed because it's moving in 3 dimensions. So if it was moving in if you have one particle moving in 1 dimension, at least in the case of the ideal gas, it's just h. But here it turned out to be 2h. Now, first question, did we make a mistake somewhere? So let's go back over here. Our mistake is this is square root of 2m. And this is also 2 over square root of mw. Okay, so that was the mistake. So if we go back and correct our, no, it is omega is outside. Yeah. Or square root of, yes, omega squared. So basically this is, here we have a square root, here another square root, this is omega squared, so this is 2. Pi is there. M's still cancel, omega squared gets out as omega. The only thing is square root of 4 instead of 4. So that is 2. This is again 2. So again, omega 0, as before, just turns out to be 2. So basically, in general, omega, you see, we said that omega over omega 0 for a 3-dimensional system, a 3-dimensional system will be d cubed p, d3n p, d3n q. This is omega, divided by 2 pi h bar, this is h, to the power 3n, integrated over the available phase space. And this is what we identified as omega. At least in 2 explicit examples, we had actually seen that omega 0 is 2 pi h bar. Let's do an example. Okay, this was the one-dimensional harmonic oscillator, a single one-dimensional oscillator. Well, let's do the more complicated case of many oscillators. both classically and quantum mechanically. Let's start with the quantum mechanical treatment. Now, let's assume we have an isolated system with energy E. This is our macro state. Now the question is, how many microstates are there corresponding to this macro state? Well, let's see, one-dimensional oscillators will be a bit simpler. Or even a three-dimensional is not a real problem. So if you look at a single harmonic oscillator, its energy would be just h bar omega. Let's assume it's isotropic. If it's not isotropic, the omega will be different in each direction. Nx plus ny plus nz plus 3 over 2. This will be the energy of a single bond. Now the total energy of my system will be just sum over all these. Sum over I from the first particle to the nth particle. I'm just summing over the energies of all the particles. Now let me define M to be E minus E over h bar omega minus 3n over 2. Now why did I define this? Because with this, M just becomes I from 1 to n, nxi plus nyi plus nzi. So the question of counting the microstates corresponding to a given energy E now just became how I have this integer m. I have to write this integer m as the sum of 3n integers. In how many different ways can I do that? So this is our question. Because this number will tell me how many microstates corresponding to a given M. Any ideas? Well, let's get the problem from any suggestion. Let's get the problem.
No, I don't have answers.
Okay, let's look at the problem in a slightly different perspective. Let's assume we have M spheres. And let me insert 3n separators. Or more precisely, 3n minus 1 separators. Well, now I wrote M as the sum of 3n integers. You see, with this separation, M is Well, in this segment there are two of them. Here there is one. In this interval there is none. Here there is one. In this space between these two separators there are none. In this space there are none. Here there is one. And here there is two at the end. Not 3 and integers. So I can find these possible values of integers by just taking these 3 and m spheres and putting some separators, 3n minus 1 of them. So now the question is this one. In how many different ways can I order these spheres and separators? Omega corresponding to this m, which corresponds to my given energy. How many objects I'm ordering? Well, so I can just shuffle them. And every shuffling will have some spheres, and in between there will be these separators. And every shuffling will give me m as the sum of 3 and integers. So the question is, in how many ways can I shuffle these objects? How many objects do I have? I don't have m. I have m plus 3n minus 1 objects that I'm shuffling. Now, among all these objects, I can order them in this much factorial different ways. But you see, if I order the spheres among themselves, if I shuffle only the spheres among themselves, it doesn't give me a different, let's say, partition of m. If I only shuffle the spheres, it will give me exactly the same partition of m in terms of exactly the same integers. So that doesn't give me a new microstate. Now, in how many ways can I shuffle the spheres? I have m of them.
Are you going to divide it by m factorial?
Yes.
3n minus.
And if I also shuffle the partitions among themselves, it doesn't give me a new expression for m in terms of different integers. It will correspond to exactly the same integers. So I should also divide by 3n minus 1 factorial. This is my omega m. Well, let us study the thermodynamics of this system. S was k times logarithm of omega. Well, this is k times logarithm of or 3n minus 1 factorial. Well, n is large, huge, so m plus 3n minus 1 will be huge. Typically, if we don't go very low temperatures, m will also be huge, the total energy of my system, above the ground state energy. So I can just use the Stirling's approximation for each one of these factorials. So this will be k times logarithm of m plus 3n minus 1. Let me ignore the 1. m plus 3n factorial minus logarithm of m factorial minus logarithm of 3n factorial, which will be k times m plus 3n logarithm of m plus 3n minus m plus 3n minus m logarithm of m plus m minus 3n logarithm of 3n plus 3n. So this cancels these terms. So the entropy of my system is K. Well, M, if you remember its definition, M is this one. Well, I will take E to be the energy above the ground state. So I will just get rid of this 3n over 2. I'm just shifting my ground state. So M is E over h bar omega. Plus 3n. Well, okay, before even that, this is K times M logarithm of m plus 3n over m plus 3n logarithm of m plus 3n over 3n. This is equal to K times m logarithm of 1 plus 3n over m plus 3n over m times logarithm of 1 plus m over 3n. Or K times E over h bar omega logarithm of 1 plus 3 h bar omega n over m over E plus 3n h bar omega over E times logarithm of 1 plus E over 3 h bar omega times n. So this is the entropy of my system. So what is the temperature of my system, for example? You see, one thing we see is that the entropy that we obtained in this way is already extensive. If you just duplicate your system, n over E does not change, so the term in the square parentheses does not change. And the S is just proportional to E. If you duplicate your system, this is duplicate, entropy is doubled. So it's already, we don't need to divide. If you remember when we were looking at the ideal gas, we had to divide by the n factorials, etc. Here we don't need to, because since we are considering harmonic oscillators, basically fixed, their position we can use to separate the harmonic oscillators. So we don't need to divide by the factorial of the number of harmonic oscillators. Now, if you remember what the temperature was, the temperature of the system was defined as 1 over T is equal to the derivative of entropy with respect to energy, in this case at constant number of particles. Well, let's take the derivative. This is equal to, let's say, the derivative of the first term, K over h bar omega, times all these parentheses, plus the first term, let's say the first logarithm, plus 3n h bar omega over E times the second logarithm, plus the derivative of the parentheses is, well, let's see, the derivative of this one will be minus 3 h bar omega n over E squared divided by 1 plus 3 h bar omega n over E minus 3n h bar omega over E squared times the logarithm plus 3n h bar omega over E times 1 over 3 h bar omega n over 1 plus E over 3h bar omega n. This is the inverse temperature. Well, let's do some simplifications. This term will cancel this one. There you go. So 1 over T. K over h bar omega logarithm of 1 plus 3h bar omega n over E. So here, let's see. Let me write the first term, or plus ke over h bar omega, or let me multiply with e everywhere. This will cancel this one, and it will also cancel this one over there. Minus 3h bar omega over e divided by, well, let me also make some simplification over there, 3h bar omega over e plus 3h bar omega n. This is the first term. Plus 3nh bar omega times 1 over e plus 3h bar omega n. Now h bar omegas, I can also cancel those. So this is k over h bar omega logarithm of 1 plus 3h bar omega n over e. Or let me write it in a slightly different way, h bar omega times 3n over e plus k over e plus 3h bar omega n times 3n minus 3. This is the inverse temperature. Now the temperature will be 1 over this. Well, let's do a simplification. You see, if you remember, when we were discussing identical particles, we said that the classical behavior should be restored if the probability of having more than one particle in the same state is negligible. So no two particles should be in the same state. That is when we restore the classical behavior. Now in this case it would correspond, remember we have an energy E which is distributed among all 3n particles. So this E over 3n harmonic oscillators is the average energy for a harmonic oscillator. Now if the energy corresponding that the system has is much larger than 3n h bar omega, then the probability of having two harmonic oscillators at the same with the same quantum numbers will be negligible. So we will be basically distributing, if E is compared to, let's say, if E is 3n h bar omega, then the most probable configuration will be basically all of them will have 1 h bar omega. If E is smaller than 3n h bar omega, that means a significant number of them should have the quantum number 0. They should be at the same quantum number. Only if E is much larger than 3n h bar omega, then the probability of having two harmonic oscillators with the same quantum numbers will be negligible. So this ratio should be much, much larger than 1. Well, that means this ratio over here is almost 0. Well, that means that we can ignore this one compared to E, because E is much larger than 3 and h bar omega. So the inverse temperature, well, if this is 0, logarithm of 1 is 0, and here we have k over E times, well, let's just ignore this 3 compared to 3n. 3n is huge. E is equal to 3n kt. Or let's write it in a slightly different form, 3n times 2 times kt over 2. This is the energy of a classical system of harmonic oscillators. Well, the reason why I wrote it in this form is this is an example of what's called the equipartition theorem. Which basically states that if the Hamiltonian, the sum of quadratic terms, then the energy of this, the average energy of the system, let's say, okay, let me not use E but H, is the sum of quadratic terms, the squares. Then E is equal to kt over 2 times the number of quadratic terms. Or this is a classical theorem. Well, let's look at over here. This is the kt over 2 is the kt over 2 appearing in the equipartition theorem. We have 3n particles, and each one of corresponding to each one of these particles, there are 2 quadratic terms, the p squared term and the q squared term. So it's just kt over 2. It doesn't depend on, for example, the frequency, whatever the frequency is, so it's still kt over 2. Well, of course, there is a frequency dependence if the quantum mechanical effects start to be important. Like if the energy is not high enough, or the temperature is not high enough, then you start seeing the quantum mechanical effects. That is the effects that are proportional to h bar, or in this case, omega. Well, let's try to, okay, so what we had done, basically, we started with the quantum mechanical description of the system. And then we said that, okay, so let's just, we obtain the entropy, and from the entropy we could find the relation between the temperature and the energy of the system. What should we do if it was a classical system? Well, I'm not sure if we will be able to evaluate it explicitly, analytically, but let's give it a try. First of all, omega is the 3np, the 3nq. And keep in mind that we have sum over all the particles from 1 to n of pi squared over 2m plus, let's say, 2me plus qi squared over 2e over m omega squared. This sum should be 1. Or, no, let me just move the e over there. Let me keep e as e. This should be less than or equal to e plus delta over 2, and larger than or equal to e minus delta over 2. Let me first define some new coordinates. P tilde, P over square root of 2m, Q tilde, Q over square root of 2 over m omega squared. So now my phase space volume is actually d3n p tilde, d3n q tilde, multiplied by square root of 2m. I have 3n of them, and square root of 2 over m omega squared. I have also 3n of them. This is my omega. And now my constraint is, my volume is defined by this relation. Now omega is, well, this m will cancel this m, so I have 2 over omega to the power 3n let me say d to the power 6nx, such that the radius in this, well, you see, this equation over here is nothing but an equation of a sphere in the 6n dimensional space. So it's I'm integrating, I need to calculate the volume of the 6n dimensional shell. R should be between e plus delta over 2 and square root of e minus delta over 2. So this is equal to 2 over omega to the power 3n. Well, here I have the radial distance to the power 6n minus 1 dr from 0 to, no, not 0, from e minus delta over 2 to e plus delta over 2, multiplied by, well, let me write it as omega 6n, the total solid angle in 6n dimensions. So omega is 2 over omega. Okay, so let me just change my, again, notation slightly, it will get confusing. So this is the volume in phase space. To the power 3, and here I have r to the power 6n over 6n, r ranging from e plus square root of, or let's say r squared cube, r squared to the power 3n, where r squared changes from e minus delta over 2 to e plus delta over 2, multiplied by omega 6n. So this will be 2 over omega to the power 3n. Well, I can just make an approximation over here. 3n times e to the power 3n minus 1 multiplied by delta over 6n times omega 6n. I just made a Taylor expansion in r squared. Around r squared is equal to e. Well, okay, so let's see, this cancels this. I have a factor 2 over here. So this is 2 over omega to the power 3n, e to the power 3n, delta over e, and 6n dimensional solid angle. That we had already calculated, the solid angle in an arbitrary dimensions. Let's see here. So this basically tells me that in six-dimensional total solid angle will be twice times pi to the power 3n divided by gamma 3n. So the volume available to my system is 2 over the frequency to the power 3n, e to the power 3n, delta over e times, here I have a factor 2. So that 2 will cancel this 2. I have pi to the power 3n divided by gamma 3n. Now the entropy of this system will be k times logarithm of this omega over omega 0, which will be k times logarithm of omega minus k times logarithm of omega 0. This is k times logarithm of, let us see, delta over e plus 3n logarithm of 2 pi e over omega minus logarithm of gamma 3n minus logarithm of omega 0. This is the entropy we have. Well, you see, delta over E will be some small number. Let's say 10 to the power minus 20. Delta is the uncertainty in our energy, or the non-conservation of the energy, whichever one you prefer. 10 to the power minus 20 is a very small number, delta over E. But when you take the logarithm, it's just minus 23. You see, here we have a logarithm which is multiplied by 10 to the power 23. So that minus 23 will be just negligible. Ignore. So the entropy of this system in this classical approximation will be k times 3n logarithm of 2 pi e over omega minus 3n logarithm of 3n plus 3n minus logarithm of omega 0. I use the Stirling approximation for gamma 3n. Gamma 3n is just 3n minus 1 factorial. But if you remember, in fact, we also had that minus logarithm of gamma 3n for our quantum mechanical treatment. We could have also just cancelled those two. K times 3n logarithm of 2 pi e over 3n omega plus 3n minus logarithm of omega 0. This is the entropy of this system in this quantum mechanical in this classical treatment. Now let's look at what the entropy was in the quantum mechanical treatment. Let me just multiply out everything first. K times e over h bar omega logarithm of 1 plus 3 h bar omega n over e times 3n logarithm of 1 plus e over 3 h bar omega n So these should be basically equal. Now, also keep in mind that you see, quantum mechanical effects will be important in a certain limit. In the limit that we can 3h bar omega n is much smaller than E. Well, let's see what that will give us. K times E over h bar omega. Well, this is very small, so this is 3h bar omega n over E, approximately, plus 3n logarithm of 3h bar omega n plus E over 3h bar omega n. This is K times, well, here h bar omega is cancelled, this one's cancelled, 3n plus 3n logarithm of E over 3h bar omega n plus 3n logarithm of 1 plus 3h bar omega n over E. Again, this is K times 3n plus 3n logarithm of E over 3h bar omega n plus 3n times 3n h bar omega over E, which should be equal to this one over here, K times what was the expression? This one. You see, this term is small, so we can actually ignore that one. It will be just a correction to the classical behavior. Well, this term is basically over here. So what this expression tells me is that you see inside the logarithm here, with this 3n factor, inside the logarithm I have E over 3h bar omega n. This should be equal to, in this expression, I have 2 pi E over 3n omega times this omega 0 to the power 1 over 3n. These two should be equal. Now e's cancel, these 3n's cancel, omegas cancel, which tells me that omega 0, this volume corresponds to a point corresponding to a microstate in phase space raised to the power 1 over 3n should be equal to 2 pi h bar, or h, or omega 0 is h to the power 3n. Three, because we are looking at three-dimensional oscillators, and because there are n of them. And again, so we already had seen this in the one-dimensional harmonic oscillator case, so this is the three-dimensional analog. So in the harmonic oscillator at least, and the free particle, we know that each point in phase space doesn't really correspond to a microstate, but a volume of h to the 3n corresponds to a given microstate. So if we want to count the number of microstates, we just need to find the volume in phase space and divide that by h to the power 3n to get the number of microstates. In the classical treatment, this won't be always correct, as we had seen here. You see there are I mean, we obtain this correspondence only in this limit that E is much, much larger than 3h bar omega n. That is the limit necessary where the quantum mechanical effects will be negligible. Now, when quantum mechanical effects becomes significant, we cannot really use this classical description anyway. But if we are treating the system classically, every microstate will correspond to some finite volume. That will give us the correct number. If we choose the volume to be this much, then that will give you the correct numerical value. Any questions? Tomorrow I will be a bit late, so let's start the lecture around 10. Not 9:40, but 10. And then we will just have one block. So see you tomorrow.